Welcome to Lecture 2. Today, I'll move from the physical acquisition of medical images to the mathematical modeling of the data itself. We'll focus on representing tissue intensities probabilistically, which is a foundation for automated segmentation and computer-aided diagnosis. For lung segmentation, the goal is to isolate the lung fields from the surrounding chest wall and mediastinum. Pixel brightness provides an important clue, since air-filled lungs typically have a distinct intensity profile, but intensity alone is not enough when boundaries are complex. A robust segmentation method combines three complementary models. The intensity model captures the expected gray level distribution for each tissue class. The spatial interaction model uses the fact that neighboring pixels or voxels usually belong to the same tissue because anatomical structures are spatially continuous. Finally, the shape model imposes expectations about the anatomical form of the object, helping prevent unrealistic segmentation results. The pipeline shown here brings these stages together, from the MRI image through spatial and shape constraints to the final mask. We then compare that mask with expert annotations using the dice coefficient, which measures the overlap between the predicted and reference regions. This is the same evaluation metric you will use in your first project. Here, I'm focusing on the core problem behind statistical image segmentation, separating different tissue types based on their gray level behavior. Consider a CT chest slice containing two dominant regions, lung tissue, labeled as Class 1, and chest wall tissue, labeled as Class 2. The challenge is to separate these regions automatically without relying on manually drawn boundaries. To do that, I need to estimate the gray level probability distribution for each tissue class. In practical terms, if a pixel has gray level value Q, I want to determine how likely it is that this value came from the lung class, and how likely it is that it came from the chest wall class. The overall process has three steps. Start with a CT image, define the two tissue classes, and estimate a distribution function for each one. These distributions then provide the statistical basis for classifying individual pixels. So, the key idea is using intensity distributions to decide which tissue class each pixel most likely belongs to. This forms a foundation of statistical image segmentation. Intensity models describe how pixel gray levels are distributed in a medical image. There are two main approaches, and the key difference is whether we assume a specific mathematical form in advance. Parametric estimation assumes a known analytical model, such as a Gaussian distribution. This is useful when tissue intensities appear approximately bell-shaped. The Gaussian model is controlled by two parameters: the mean, which identifies the center of the distribution, and the variance, which describes how widely the values are spread. Together, these parameters determine the probability assigned to each gray level value. Non-parametric estimation makes fewer assumptions. Instead of selecting a fixed formula, we estimate the distribution directly from the observed pixels. The most common method is a histogram. It counts how many pixels occur at each gray level value, producing an empirical approximation of the intensity distribution. So, parametric models are compact and interpretable when their assumptions are reasonable, while non-parametric methods can capture distributions that do not fit a simple predefined shape. In practice, the choice depends on how well the image data match the assumed model. This slide highlights a fundamental choice in medical image analysis: whether the tissue classes are estimated with labeled examples or discovered directly from the image. The key distinction is the availability of labeled training data. With supervised estimation, an expert provides representative samples for each class. For instance, a radiologist might manually select pixels that belong to the lung and other pixels that belong to the chest wall. The algorithm then uses those labeled samples to estimate an intensity model for each tissue class. When the labels are accurate and sufficiently detailed, supervised methods are generally more precise because the system is guided by known examples. Unsupervised estimation takes the opposite approach. No labeled training data are supplied, so the algorithm must identify likely tissue classes by analyzing patterns within the image itself. It may use clustering, mixture models, or related statistical learning techniques to separate those groups. This is especially valuable when manual labeling is difficult, expensive, or simply unavailable. The trade-off is that the discovered groups may require interpretation, since the algorithm finds patterns without being told exactly what each tissue class represents. This slide introduces supervised parametric intensity models, a method that uses labeled image regions to learn how different tissue classes appear in terms of gray level intensity. The process begins with training samples taken from a CT chest slice. Here, the two classes are lung, labeled class 1, and chest, labeled class 2. The first step is to extract the gray level values from manually selected regions. Each tissue class contributes its own collection of samples. For the lung, the examples include values such as 98, 85, 105, and 61. The chest region provides a different set, including values such as 130, 133, 207, and 168. These samples represent the observed intensity behavior of each class. The second step is to select a probabilistic model for each class. The model should reflect both the physical characteristics of the imaging modality and the statistical behavior of the tissue. Once those models are estimated from the labeled samples, they can support classification of unlabeled pixels or regions in the medical image. This slide continues our discussion of supervised parametric intensity models by organizing probability distributions into two broad categories, continuous and discrete. The key distinction is whether the modeled intensity can take any value across a range or only specific countable values. For continuous data, the table lists familiar models such as a Gaussian or normal distribution, along with exponential, gamma, Erlang-K, chi-square, Weibull, Rayleigh, uniform, beta, and Cauchy distributions. It also includes Rickian and Nakagami models, which are additional choices within continuous family. These distributions can provide different mathematical descriptions of intensity behavior. For discrete data, the listed options include Bernoulli, binomial, Poisson, hypergeometric, geometric, and Pascal, also called a negative binomial distribution. The table also includes a discrete uniform model and multivariate models. In practice, selecting an appropriate distribution is part of building the parametric model. The choice depends on the type of intensity values being represented and on which probability assumptions best describe the data used for supervised medical image analysis. The probabilistic model should be chosen from the behavior we actually observe in the training data, rather than selected arbitrarily. The practical process is straightforward. First, collect the gray level values from the training region. Then calculate their histogram and examine its overall shape. That shape provides the main clue for model selection. A symmetric, bell-shaped histogram suggests that a Gaussian model may be appropriate. If the values are strictly positive and noticeably skewed, models such as gamma, exponential, or Rayleigh may provide a better fit. When the data represent discrete counts, such as photon counts in nuclear imaging, the Poisson model is a logical choice. In many CT soft tissue examples, the histogram often looks reasonably close to a bell curve. For that reason, the Gaussian model is a useful first approximation. It is still important to treat this as an evidence-based starting point and to compare the model's theoretical shape with the observed histogram before relying on it for further analysis. In MATLAB, a digital image is handled as data, specifically a two-dimensional numerical array or matrix. Each matrix element represents one pixel. Its row and column identify the pixel's spatial location, while its numerical value describes a pixel's gray level intensity. The example on this slide uses a simple 4x4 matrix with only 4 possible intensity values, 0, 1, 2, and 3. A value of 0 represents the lowest intensity in this example, and higher values represent progressively brighter gray levels. The arrangement of those values across the rows and columns forms the image's spatial pattern. This representation is important because it turns an image into something MATLAB can calculate with directly. We can examine individual pixels, apply mathematical operations, compute an intensity histogram, and estimate models that describe the image's gray level distribution. In medical image analysis, that provides a foundation for processing and interpreting images systematically, rather than treating them only as visual objects. The table shown here is therefore a compact numerical description of the corresponding image. This slide illustrates how we build an image histogram from a simple grayscale image. The example matrix contains 4 possible gray levels, 0, 1, 2, and 3. To create the histogram, I scan the matrix and count how often each value appears. In the 16-pixel example, gray level 0 occurs 5 times, gray level 1 occurs 4 times, gray level 2 occurs 3 times, and gray level 3 occurs 4 times. Those counts form the histogram, showing the frequency distribution of image intensities. The important idea is that the histogram summarizes the image without preserving the location of individual pixels. It tells us how common each intensity is, which can help reveal whether an image is mostly dark, mostly bright, or spread across a broad range of gray levels. More formally, this is a non-parametric estimate of the image's intensity distribution because it is derived directly from observed pixel values rather than from an assumed model. We can also use it to estimate empirical probabilities or to select and validate a parametric probability model. To calculate an image histogram in MATLAB, one basic and instructive approach is to use the find function. This function searches a matrix for elements that meet a specified condition and returns their locations. For example, to count pixels with gray level 0, we search the image matrix for elements equal to 0. MATLAB returns the row indices and column indices of the matching pixels, along with non-zero indicator for those matches. The number of pixels at that gray level can then be found by measuring the length of the return index array. In other words, the length tells us how many times gray level 0 occurs in the image. We can repeat the same process for every possible gray level to build a complete histogram. This method is useful because it makes the basic construction of a histogram easy to understand. However, for large medical images, MATLAB's built-in histogram functions are generally faster and more efficient. The accompanying file snippet_01_image_histogram.m provides a reference for this implementation. This slide applies the histogram concept to a real CT chest slice, where the goal is to distinguish 2 major tissue regions, the lungs and the chest wall. The lungs contain a significant amount of air, so their pixels generally have lower gray level values. The chest wall contains denser tissue, producing higher gray level values. If we plot the intensities from each region separately, the lung histogram tends to cluster toward the lower end of the grayscale range, while the chest histogram shifts toward higher values. Each distribution can be approximated by a Gaussian-like curve, which gives us a useful model for comparing the 2 classes. The important limitation is that these curves may overlap. That overlap means some pixels have similar intensity values even though they belong to different tissues. So, intensity alone may not be enough for a perfect segmentation. When that happens, we can improve the decision by incorporating spatial relationships between neighboring pixels, or by using shape models that describe the expected structure of the lungs and chest region. Once the probability model has been selected, the next step is to estimate its parameters using the training data. For a Gaussian model, those parameters are the mean, mu, and the variance, sigma squared. The mean describes the average gray level value for a tissue class, while the variance describes how widely the sample values spread around that average. To estimate the mean, we add the gray level values from the training samples and divide by the total number of samples, n. The variance then measures the square differences between each sample and the estimated mean. Because variance is calculated from a sample, the denominator is n-1. This process is performed separately for each gathered class. In the example shown, the classes are lung tissue and chest tissue from a CT chest slice. That give the model a distinct statistical description for each class, rather than treating all pixels as if they came from the same distribution. In MATLAB, the calculations are implemented directly with the mean and var functions, making the parameter estimation step concise and reproducible. This slide summarizes the training statistics used to build intensity models for the lung and chest regions. The training samples are gathered automatically from the image using threshold-based masks, although the fully supervised version can use masks drawn by an expert. For each tissue class, the analysis records the number of pixels, the average intensity, and the variance, as shown in the table. The most important observation is the separation between the two means. The lung class contains about 110,690 pixels, with mean intensity of 89.139, while the chest class contains about 151,450 pixels, with a much higher mean of 202.38. This difference is expected because air-filled lung tissue appears darker in the CT image, whereas denser chest wall tissue appears brighter. The variances are relatively similar at 1,399.8 for lung and 1,010.8 for chest. That supports modeling the two classes with Gaussian distributions that have different means. In practice, the mean difference becomes a primary feature for separating lung from chest using intensity alone. This slide presents the output stage of the training data analysis for lung and chest images using a threshold-based approach. The focus is on comparing the original CT scan with its corresponding mask, so we can see how the image data and the segmented lung region relate to one another. The key idea is the connection between the CT scan and the mask. The CT scan contains the medical image information, while the mask identifies the region being analyzed or extracted for training purposes. The slide also points to the MATLAB file, snippet_02_estimate_lung_intensity_models@m, as a reference implementation for this step. That reference is important because it provides the method behind the output, rather than treating the displayed result as an isolated visual. Since this is labeled as an output with a threshold, the intended interpretation is to examine how the selected threshold separates relevant lung or chest regions from the rest of the scan. In practice, the CT and mask should be reviewed together to assess whether the resulting training data captures the intended anatomy consistently. This slide shows how training data statistics are estimated when a manually drawn binary mask replaces the thresholding step. The key idea is that the mask defines the two classes directly and precisely. The white region, Class 1, identifies exactly which pixels belong to lung and are used to estimate the lung Gaussian model. The black region, Class 2, is simply the logical complement, and its pixels are used to estimate the chest Gaussian model. Importantly, only the data collection step changes. The parameter estimation and plotting procedures remain the same as in the threshold-based approach. This makes the method easy to compare while improving the quality of the input data. The lung statistics are no longer influenced by background or relevant tissues, and the resulting class means and variances are more accurate and reproducible. This approach also reflects clinical practice, where radiologists commonly delineate regions of interest. Because the mask selects different pixels, the estimated parameters change, and the two Gaussian curves update automatically. The reference MATLAB file demonstrates this mask-based workflow. This slide presents the output of the training data statistics for lung and chest CT images, with their corresponding masks. The focus is on understanding the relationship between the original scan and the region identified for analysis. On the slide, the two key elements are labeled CT scan and mask. The CT scan represents the medical image itself, while the mask indicates the selected or relevant area within that image, such as a lung or chest region being examined. This pairing is important because image analysis models typically need both the input image and a defined target region to learn from. The slide refers to the MATLAB script, snippet_03_estimate_lung_intensity_models_with_masks@m, which is associated with generating or estimating these statistics using mask data. So, the main takeaway is that this output is organized around mass CT data, providing the basis for analyzing lung intensity patterns, while keeping the region of interest clearly defined. The scripts are available on GitHub at GitHub. com/Hassan/B544 Artificial Intelligence Techniques in Digital Histopathology. You can access the repository there to review and download the materials. This concludes the BE640 medical image analysis presentation.